It is the top of the hour, so we will work on coming back. I'll give everybody just another minute, and that way we can also ensure that our recording started. So get settled, and we'll start in 1 minute. All right, let's dive into Introduction to Radiation Sterilization. So we've started out, we have kind of our foundation talking about microbiology. So we have our bioburden and our sterility testing. It is a little bit drinking from a fire hose, so let's jump into Introduction to Radiation Sterilization and start tying our foundation into our sterilization modality. So why radiation? Well, radiation tends to work very well for almost all plastics. We can sterilize PTFE and Teflon if we keep the doses low enough and depending on product functionality and purpose. We generally can sterilize circuitry as long as, again, we can keep the dose low enough and depending on functionality and complexity. Radiation sterilization is one of your few options for liquids. So radiation sterilization can do liquids, and that can include drugs, liquids as well. We do drugs and pharmaceuticals that can be bulk sterilization for active pharmaceutical ingredients, APIs, tissue and tissue-based products, so our biologics. And one of the advantages with radiation is we have no residuals. So one of the things that you need to consider is all sterilization has advantages and disadvantages. So one of the questions that I like to ask is, what is the best sterilization methods? Well, of course, I'm biased towards talking about radiation, but the reality in practice tends to be steam or moist heat sterilization, because generally speaking, it's very quick, it's affordable, there's really no residuals left behind. So why doesn't everything do steam sterilization? Well, because you end up with a pile of goo in a lot of situations. So functionality really matters when it comes to which radiation sterilization method as well, and which sterilization method overall that you are going to take a look at. So one of the advantages with radiation is we don't have residuals, but you do need to consider your functionality and the effect to product. And with every sterilization method, you have to look at that functionality for the product, but also its packaging system. So one thing to keep in mind with radiation sterilization and all sterilizations is there is no sterility without a sterile barrier. If there's no sterile barrier system, the second I remove it from the sterilization source, it's essentially exposed to the environment and potentially no longer sterile. So when we're talking about functionality, it's also important to consider the packaging in our sterile barrier system that we're in. So radiation, we don't have to worry about ethylene oxide residuals. We don't have to worry about hydrogen peroxide residuals or things like that from others. But we do want to make sure that we consider what our functionality of our product and our packaging system are afterwards. And generally speaking, radiation, when it comes to material compatibility and functionality, It's not it's compatible or it's not. That tends to be the way it works for something such as ethylene oxide, not so much for radiation. Generally speaking, with radiation, the more dose, the more potential effect there is to materials and product. The less dose, the less effect that we're potentially going to have. So, with that kind of in mind, radiation, generally, we're kind of the good guys. So, we are able to handle those liquids, and we do have products that we can handle that other sterilization modalities can't really do. So, radiation is the solution to various problems in a lot of situations. So, let's talk about what we're going to go over in this module. So, we're going to talk first on building a foundation. So, we're going to talk about our types of radiation. And then we are going to talk some more about bioburden testing, especially the recovery efficiency. And then we are going to talk about our verification doses. What are they? What do they mean? And what are they for? We're also going to talk about sterility testing, and we're going to go into a little bit more detail on the method suitability and the BF testing so that we can tie that together. And then we're going to talk about our validation methods. So what are our options for validating for sterilization? So we kind of touched on it a little bit in the previous. So for example, we were talking about verification doses. I threw out the terms VD max and method one. So we're going to see what those validation methods actually are, what they mean, and kind of why one versus another. And then we're going to get into what I kind of consider myself the fun stuff. So, our family groupings and our product families. So, we don't want to have a sterilization validation for each and every individual product. That's really not practical in a lot of situations. So, we're going to talk about how we can build sterilization families and family groups. And then, once we have a family group, we can adopt products into those families. So just like we have a human family, we also have our uh, sterilization families as well. Yes, Todd.
I just pointing you, there's one question in the chat there.
Yeah, let me pull that up. So the question is, for clarification, when you say go to zero, you are referring to log zero or one. So generally speaking, for radiation sterilization, we can't exactly go to zero. We can go to population zero. That's generally more for biological indicators. For radiation, we're actually going to go to a 10 to the minus 1 sterility assurance level or a 10 to the minus 2. So we'll kind of see how that works out as we go. So let's start off with some terminology so that we can make sure that we all have the foundation of some of the words that we're going to be using today. So the first is radiation, which is either in the form of energy or waves. In the case of gamma and X-ray, that's generally going to be our gamma rays and our X-rays, or in the form of subatomic particles such as electron beam. So as the name implies, it is literally a beam of electrons. So we have the electron subatomic particle that we are essentially shooting a beam of in order to sterilize the product. So radioactive is a substance that emits radiation. So generally for gamma, that's going to be our cobalt 60. For X-ray and for E-beam, that's going to be our accelerator-based methods. So irradiation and irradiated means it's exposed to radiation. And this is one of the common misconceptions that tends to be out there is irradiation really just means exposed to radiation. So everyone right now at this very moment is being irradiated. To an extent, you're being irradiated by your screen, your monitor, however you're watching this. You're being irradiated by the sun right now, unless it's nighttime where you happen to be. But you're being irradiated by the sun. You're being exposed to that radiation. So irradiation just means exposure to radiation. There is a difference between irradiation and what we refer to as induced radioactivity. Just because I irradiate something does not mean it becomes radioactive. In order for something to become radioactive, there has to be a nuclear, meaning an interaction with the atomic nucleus interaction. So gamma and X-ray, since they are waves, they actually don't have any sufficient energy to actually cause that atomic interaction. So whatever my atomic number is going into that chamber is actually going to be the same coming out of that chamber. So my product when it goes in is no more radioactive coming out than it was going in. There is no induced radioactivity. So electron beam, I do have a subatomic particle, and if I accelerate it sufficiently, that electronic particle can have a nuclear interaction. The thing is, it is an electron, and I need to have a nuclear interaction, meaning I need to have something interact in the nucleus, which is where the protons are. These are opposing charges and they repel each other. So unless I have the electron beam turned up really, really high, I'm not going to have any induced radioactivity. And that's something to be very mindful of is your electron beam is going to make sure that their systems, their processes are such that they are not causing induced radioactivity to your product. Generally speaking, the beam is nowhere near powerful enough to actually cause that induced radioactivity. So irradiated just means exposed to radiation. Then we have our ionizing radiation. So that is radiation capable of removing electrons from the atoms or the molecules. So we are creating ions, cations, for example, anions, but ultimately we're causing chemical interactions on the molecular level. We're not changing the actual atom. We're just causing ionizing radiation, which is interaction with the electrons of that, which ions is essentially chemistry. So that's really all we're doing is we are making and breaking hydrogen bonds generally. So our radiation modalities, which is our types of radiation. So when we talk about a sterilization modality, we're talking about the form of sterilization. So that would be gamma, E-beam, X-ray for radiation. If we're just talking sterilization modality in general, that's going to be your radiation, EO, steam, for example. So our three modalities for radiation are gamma, E-beam, and X-ray. Those are what you're going to see. So gamma is like you see there with our glowing blue cobalt. So X-ray is going to be accelerator based, so it's actually the same as an electron beam. So we have an electron accelerator. So for example, in the bottom left there, we have what's known as a rototron, and that is going to accelerate our electrons and form them into a beam. That beam then goes through a scan horn, which is there on the bottom, and that is going to basically scan across the product and going to scan the beam for sterilization. The difference with X-ray is we're going to take that electron beam and we're going to crash those electrons into a plate, a converter plate. And then that is going to convert the electron beam into X-rays. And that's where we get our X-ray sterilization. So a lot of times electron systems will be what we call dual source, where they're going to be set up to do both E-beam sterilization and X-ray. So let's kind of take a look at how that works. So for gamma sterilization, we have what is known as shuffle and dwell. So product is going to be loaded onto carriers. So we have our boxes of individual product, for example, kind of illustrated, and that is being loaded into a set carrier. That carrier is then going to be loaded into this pathway into the gamma irradiator, and it's going to go into various positions, and it's going to dwell there. So basically what we have is in the middle here, we have that source rack that we saw on the previous slide, where we basically have a panel of cobalt-60 that is giving off radiation. And then we're surrounding that radiation with our various carriers. So a good way to kind of think of it is we basically have kind of a campfire here in the middle, and we're absorbing the energy from that campfire by sticking these carriers in various positions. they're going to shuffle to different positions, and they're going to dwell over time. So for gamma, generally speaking, our dose is directly correlated to time. The more dose we need, the more time it's going to spend in the chamber. The less dose we need, the less time it's going to spend in the chamber. But we're going to go through this overall shuffle and dwell process. Now, something to be considerate of is my product, if I'm loading it into the chamber, can't go any faster than the product in front of it. So if I need less dose, then that's going to be a problem because I need to go through the chamber faster, but I can't go through the chamber any faster than the product in front of me. So there's going to be some different cycles. Similarly, if I have a product that needs a really high dose, I can't just sit and dwell around forever and have a low dose product coming behind me. I have two different timing sets. So as we talk about radiation, kind of be mindful of this in the back of your head because we have dose ranges that we're going to kind of talk about. And the more dose ranges I have, the more of these cycles I can fit into. Because what the irradiator is going to do is they're going to kind of group and they're going to clump their low dose products and they're going to run them together. And then they're going to group and they're going to clump together their higher dose products. If I have a product that has a very large dose range, so let's say something, for example, of like 20 to 50 kilogray, I have extra room that I can basically fit into more cycle options. The more cycle options I can fit into, the more cycles are available to my product. Likely, the faster my product is going to be able to be processed through that irradiator, and that's going to improve my turnaround time. So we want to kind of give the irradiator some of that flexibility, if possible, in order to be able to fit into some of those additional cycle options. So gamma irradiator, kind of our process variables is the irradiation pathway. That's generally going to be controlled by the irradiator themselves though. So then our cycle time, again, the longer I sit in the chamber, the more dose I can absorb. The less time I sit in the chamber, the less dose I can absorb. So load configuration, how my product is loaded into that carrier is going to change how much dose I can receive or not receive. More product generally means I have more material to absorb that dose, but that also means that there's kind of less dose in different parts of that container. So I may be causing some issues potentially there. So density is kind of one of our big considerations when it comes to irradiation. So that is therefore one of our variables when it comes to load configuration and also mixing of products. So if we kind of go back to our video, the carrier that we are using might then be followed by a completely different company's carrier in what they're using. So we do have some variability in that we have mixed product going through, and we also have the option to send mixed product through ourselves. So depending on our dose map, we may be able to send more than one type of product through the irradiator so that we can kind of maximize what we're loading into our carrier. Because generally speaking, for gamma, we're paying on a per carrier basis. So gamma generally, time-wise characteristics is that it's on the order of several hours. So for example, depending on what we refer to as hot or cold with our source, the hotter the source is, the less time it has to sit in. But kind of, for example, a typical amount of time through a normal gamma irradiator is likely to be on the order of several hours, for example, say 8 hours. So from the time my product is loaded into its carrier until it's coming back out and getting unloaded from the carrier, may be on the order of, for example, about 8 hours. So heating is non-adiabatic. So what does that mean? Well, because dosing is over such a long period of time, every sterilization, thing to keep in mind is every sterilization method, every single one is taking energy and adding it to the system in order to inactivate microorganisms. In the case of ethylene oxide, that energy is chemical energy as well as some thermal energy. When it comes to steam sterilization, we're talking thermal energy, liquid chemical sterilization, of course, chemical energy. So with radiation, we're talking about that ionizing radiation. And with that energy, we generally have a temperature change. So some chemical reactions are endothermic, some are exothermic. Well, when we're pumping energy into the system, a lot of times we're pumping heat into the system with that. But since radiation is over the course for gamma of several hours, that generally means that the energy going in also has plenty of time to go back out. So generally speaking, I'm not going to see a big temperature rise with gamma irradiation. So heating wise, I generally don't have a big temperature change with gamma. So also with that, again, we can irradiate different types of product can be radiated together, and density is gamma isn't as sensitive to density. So it's a very robust, proven technology, and it does lend itself well to standardization for some of the various things. So gamma is kind of our first. So our next is electron beam. So, as I kind of mentioned, an electron beam is literally just that. It is a beam of electrons that is being accelerated and shot into the product. So, what you have here kind of being illustrated is you have the scan horn that's scanning up and down. Now, for the animation, we're showing it fairly slow. It's actually so fast you can't see it, but it's basically scanning and what we call painting the target with that electron beam. So it's very directional in that it is shooting uh, the electron beam into the product. You'll also notice that the carriers are much smaller. And if you notice on the left side of the screen over here, you'll notice that we do have the product being turned. So a lot of times what we'll do is do what we refer to as a double pass for electron beam. So it'll go through one time, receive half its dose, it'll get turned around, and then it'll go through and it'll receive the second half of its dose. So the comparison that tends to work very well with radiation, just like kind of on the previous slide, we could kind of think of gamma as similar to having a heat source, and then we're absorbing that by placing it in proximity. So we have our rotisserie chicken. Well, with electron beam, when we're doing this flip, it's an awful lot just like with our food, how we're flipping it over to help it cook evenly. So electron beam does tend to be a lot just kind of like how you're seeing here. It is fairly fast through the chamber. However, it is a much lower density. So we're only doing a few boxes at a time. We're only doing, for example, one or two, maybe two boxes thick. So generally, overall, even though electron beam is faster, overall throughput between gamma and electron beam tends to be comparable from one modality to another as far as throughput, because while the one's faster, it's doing less. The other one is slower, but it's doing more in bulk. So with electron beam, we do have process variable of beam energy. So they do have the ability to adjust the beam strength, so they can essentially turn it up and down. We also have cycle time, so we can control how fast it's going through the conveyor. We can speed it up and slow it down. And as before, we have load configuration. So we can change how our product is loaded into that chamber, as well as the irradiator can sometimes adjust a little bit with, am I loading 2 boxes deep? Am I loading a single box deep? So processing characteristics, electron beam tends to be seconds to minutes. So generally speaking, it's only going to be exposed to that beam for a very short period of time. But that does have some consideration that goes with it because heating is adiabatic. So again, all sterilization is putting energy into the system. So for gamma, we're doing that over the course of hours. So the amount of energy we're putting in is allowed to dissipate right back to the environment. With electron beam, we're shooting all of that energy in a very short period of time. And that energy really doesn't have time to then release back to the environment. So we do tend to see heating when it comes to electron beam that we're not seeing with gamma because of that interaction where we are just throwing so much energy into the system in such a short period of time. However, the other side of that is because it is such a fast process, there is less possibility and less potential for oxidative effects to polymers. So, in some aspects, electron beam can be more material compatible for some products because it has less of that oxidative effect. Some products are actually less material compatible than gamma because of that heating effect. So it kind of depends on what your product is sensitive to and what you're going for as far as material compatibility. Another consideration with electron beam is that density. So we need to make sure that we are presenting the same product to that beam consistently every single time. So for gamma radiation, a lot of times we may see loose product just in Tyvek pouches. E-beam, we want it very organized. So a lot of times, instead of thinking pouch, you really should think trays. And you should think not just trays, but kind of as is illustrated here, we should even consider the orientation of product within that tray. So if I have an electron beam and let's say it's scanning from the top down, I have an area of low density, I have an area of medium density, and now I have an area of higher density. And that's all going to get different doses and shadowing. Same over here. I have a large area of low density because I have this big airspace, and then I have this area of high density. And depending on how I load this in to the chamber is going to depend on how my dose is delivered. If my dose is coming down, you can see how I have a lot of low density followed by a very high. If I come in from the side, I have low density, high density, low density again. So with electron beam, it's very dependent on the density and sensitive to the density of my product. So again, instead of pouches, think trays, and don't just think trays, think how is my product loaded into the tray so that you can make sure it is loaded into the tray consistently. So one other additional consideration with electron beam is for testing purposes. Generally, we need what is referred to as a dose map. So there are two types of exposures we're going to do for radiation. We have our sterilization exposures, which is actual product being sterilized and sent to market. That's what we refer to as our sterilization or our minimum sterilization dose exposure or sterilization exposure. We also have our testing exposures. So this is where we're exposing to our verification dose at that lower sterility assurance level. Well, for gamma, generally we don't need a dose map because it's not as sensitive for that verification dosing. We will need a dose map for the larger production dosing, also called the sterilization dosing. For E-beam, we need a dose map for both. So when we're talking about testing and turnaround times for validations, do keep in mind that for electron beam, we do have to have that dose map, and that dose map takes time. So one of the questions I usually get is, well, why do I need two different dose maps for electron beam? Why can't you just use my production dose map? And the answer really comes down to the dose delivered and the configuration. When you're sending it for your industrial sterilization, for your final sterilization of finished product, you're sending cases of product and you're packing those cases as much as you can to optimize your throughput through the irradiator. When we're sending it for verification dosing, we're sending it through essentially a package at a time or one single box of product. So it's going to be a very different configuration that they're dosing compared to your industrial sterilization. Many boxes versus one boxes, many boxes with many boxes in them versus maybe a box with only 10 boxes in them for our testing purposes. The other thing is the dose delivered itself is going to be different. We might have a minimum sterilization dose of 25 kilogray and a verification dose of only 8 kilogray. Those are two very different ranges. So, and such, between the different configuration and the different dose, we tend to have that dose map. So electron beam, just kind of keep in mind configuration and orientation matter. And then for testing purposes, we likely are going to need that additional dose map. X-ray radiation tends to kind of be between the two. So it's not as sensitive to density as electron beam. It is a little bit more sensitive than gamma. But what we're essentially doing is we are taking that accelerator and we're converting it to that X-ray. So our process variables, again, we can adjust the beam energy and we can adjust how it's going down the conveyor. So we can change our cycle times. Again, we can also change our load configuration. So timing tends to be kind of an intermediate between the two, but it does tend to be more so on the order of hours and minutes rather than minutes and seconds. So heating as such, since it is a longer time, does tend to be non-adiabatic because, again, we are pumping energy into the system, but it has time in order for that to then be released back ambient to the environment. So we generally don't see heating like we do with potentially electron beam. And then as far as material compatibility and oxidation of polymers goes, again, it's kind of an intermediary. It tends to be kind of somewhere in between gamma and E-beam. It tends to be faster than gamma, so we don't tend to see as much oxidation, but it is slower than an E-beam, so we tend to see more oxidation than E-beam. It's kind of somewhere in between. So generally, just like with E-beam, dose mapping is required, and X-ray is fairly new to the market. It is growing in the market, and there is getting to be a lot more X-ray in the market, but it is still relatively new. So you likely are going to see a little bit of additional scrutiny with that. And then kind of finally, one of the last items with X-ray is it is an inefficient energy conversion. So kind of one of the ways to think of X-ray is really like an incandescent bulb. So I'm taking an electron beam, I'm shooting that at a converter plate, and then depending on who you talk to, whether you talk to the marketing people or whether you talk to the engineers versus whether you talk to the physicists, they're going to tell you different conversion rates. But ultimately, it's usually converting somewhere between 7 and about 14% is being converted from the electron beam to an X-ray. So quite a lot of the remainder of that energy is actually just being converted to and lost as heat. So it's kind of like an incandescent bulb in that aspect. So an incandescent bulb, we throw a lot of energy in, we get a little bit of light out. Sort of similar with X-ray, we throw a lot of energy in, we get a little bit of X-ray out. So that lack of efficiency does tend to lead to some additional costs associated with X-ray. So kind of that's your three mixes. So kind of a summary and comparison. So flexible target dose, gamma, no. Generally speaking, you're just going to change your time. Field direction, gamma's going off in every direction, and we're just trying to surround and absorb that. X-ray does tend to be directional. E-beam is directional. That can have some advantages, but that also does mean that we want to ensure that our product configuration is controlled. So dose rate, just kind of like we were saying, low, medium, high. So gamma has a really low dose rate, E-beam has a really high dose rate. So one's slow over the course of hours, one's fast over the course of seconds to minutes. So here's kind of how that really matters is what is known as our dose uniformity ratio. So DUR is our dose uniformity ratio. The smaller the number, the better, because that means that our ratio between our low and our high is smaller. So that means we have a smaller dose range. So our dose uniformity ratio is low sensitivity for gamma, meaning we can change density and we can change thicknesses, and we're still going to get a nice uniform dose. Electron beam, we start changing things. We change our density, we change our thickness. That's going to really affect our dose uniformity ratio. We have seen people that have changed out their instructions for use, and they've added pages or changed the paper that it's made out of, and that can affect your electron beam and your dose uniformity ratio. So little things can add up very quickly with electron beam. So some examples of dose uniformity ratio. So gamma, for example, we have what we call a 1.66 multiplier, or to make the math simple, a 1.6 multiplier. So what that means is, let's say I have a minimum sterilization dose of 25 kilogray. Well, I can't just make every single product and every part of that product receive 25 kilogray. Instead, again, kind of going to a cooking analogy, I have hot spots, I have cold spots. So I end up with a dose uniformity ratio, which is my ratio between my hot spot and my cold spot. So if I have a 1.6 multiplier and I have 25 kilogray, my range is going to be 25 to 40 kilogray, which you've probably heard in the industry because that's a fairly common range. So for electron beam, I'm much more sensitive to my density, and as such, I tend not to have as good of a dose uniformity ratio. So we tend to see dose uniformity ratios more along the lines of a 2x multiplier, and depending on the setup, the homogeneousness, basically how dense and uniform that density is of my product, I can see dose uniformity ratios as high as 2.83 kilogray. Now, X-ray, this is where X-ray really shines, is I can adjust my beam really well. I'm not as sensitive to density and to how that density is distributed through my product, so my homogeneity. So as such, my dose uniformity for X-ray tends to be fairly low, such as a 1.4 multiplier or 1.5 multiplier. So in such an example, if I have a 25 kilogray minimum sterilization dose and I have that 1.5, instead of 25 to 40 kilogray, my product's seeing, say, 25 to 37.5, or essentially 25 to 38 kilogray. Now my product is seeing 2 less kilogray with X-ray than, for example, compared to gamma. So that drop of 2 kilogram dose may mean all the difference as far as my product's functionality, my packaging shelf life, things like that. So that's one of the places where X-ray does really shine, is its dose uniformity ratio. Gamma, its real advantage is that it doesn't have as much sensitivity to material thickness, so that density. So I can have very dense materials, or I can have density that's very unevenly distributed throughout my product. So I can have something, for example, which has a very high density, really low density, and I'm still going to get uniformity. E-beam, kind of its advantage is that oxidative effect to materials and products, and as such, some of that improved material compatibility. So when we're talking about radiation, we can't talk about it without talking about dosimetry and dose. So sterilization has processing variables. So for ethylene oxide, we have temperature, relative humidity, gas concentration, and time. So we have 4 variables for ethylene oxide. For steam sterilization, I have temperature and I have time. So I have 2 variables. For radiation, I have 1 variable, dose. So how that dose is delivered might vary, and the time to deliver that dose might vary, but ultimately all I'm concerned with is what that dose to product is. And that's therefore where dosimetry comes in. So a dosimeter is a device that has a reproducible ability for us to measure it. So for example, here on the right, these are dosimeters. The more dose they receive, the more they're going to discolor. So you can kind of see this color spectrum. So the more dose we have, the darker the coloration gets. We also have radiation indicators. These are just an indicator and they are not used to measure dose. So for example, we have what we call the red dot indicators. So those might go from yellow to red or from green to red. These do not measure the amount of dose received. So I like to kind of convey things with stories. So kind of a quick story, there is a requirement in the standards that irradiated and non-irradiated products be segregated. And it specifically calls out that radiation indicators are not acceptable. So you really need some physical tracking, such as having cages, fencing, as well as having some tracking such as batches, batch numbers, things like that. You really can't rely on radiation indicators. So the reason for that is radiation indicators aren't measuring whether the sterilization dose was delivered or not. They're just detecting whether they've been exposed to radiation or not. And that can vary. So we have received product before where the red dot indicator was red. And we don't want to test irradiated product for bioburden because that's not representative of the product's bioburden. We don't want a sterility test product that's been irradiated because that's not indicative of the verification dose and the appropriate dose. So we contacted, excuse me. So we contacted the sponsor of the study and we said, hey, it looks like you sent us sterile product for testing. We can't test sterile product. We need you to send us non-sterile product for testing. And they were very insistent that they had sent us non-sterile product for testing. And there was some back and forth. We even took photographs of the red dot indicators to very much show them, no, your product is showing a red dot, which is an indication that it's been exposed. And they were, no, it's this batch. This batch has not even been sent for sterilization yet. It's still sitting in our warehouse unsterilized. That batch can't have been exposed to radiation. Well, what we found was that their shipping had gone through Mexico, which means it had to come into the United States. And at the port of entry for the United States, their shipping container had been scanned. It had been scanned with radiation. And that radiation scanning, in order to scan the container and make sure there wasn't anything that shouldn't be in there, that scanning process was sufficient to cause the red dot indicator to turn from yellow to red in their particular case. So red dot indicators, not necessarily the best indication of whether a product is sterile or not, just whether that indicator has been exposed or not. This is also a point when I like to tell the story of make sure you do things that make sense. Now, I know that seems like it should be fairly straightforward, but we had a company that they had specifically written into their protocol that they could not release product unless the red dot indicator was on the box and red. So during their manufacturing process, there was an issue with their labeling machine, and a whole lot of product did not receive its indicator. So they asked us specifically if we could take a roll of indicator and expose it to radiation to color change it so that they could then label their product with the red dot in order for it to release. They already had the paperwork and everything indicating that, yes, this batch of product has received this sterilization dose. They knew the product had been irradiated properly, but due to their own procedures, they couldn't release it without that red dot. And their solution was to irradiate the red dot separately from the entire product and then place that red dot on the product. That doesn't exactly make sense when you have product you know is sterile and you can demonstrate is sterile. So do things that make sense, don't do things that don't make sense. So also keep in mind a radiation indicator is not the same thing as a dosimeter. It does not indicate that the product has been properly sterilized. So let's talk about that dose uniformity ratio and our dose range. So that brings us to our maximum dose testing or max dose testing. So throughout all of radiation, we're going to talk a lot about dose, and we talk about min dose and max dose and verification dose and delivered dose. So let's kind of bring that together in a bit of a visual manner in order to understand that. So when we're talking about our minimum dose or our sterilization dose, that is the minimum amount of radiation required for the product to be considered sterile. So that's basically kind of like our floor. That's the minimum that we need. But then we're going to have a processing window. Like I said, just like you have an oven, you have hot spots and you have cold spots. Same with radiation. Some product is going to receive a bit more dose, some product is going to receive less dose. What really matters with the minimum sterilization dose is we're making sure that those products that are on the minimum side receive enough radiation to be considered sterile. So if I'm making a batch of cookies and I have a cookie in the cold spot, I want to make sure that that cookie is fully cooked. I don't want to give anyone salmonella. So that's our minimum sterilization dose. Now, when I get to my processing window, I'm going to have that hot spot. So I'm going to have that processing maximum. So when I talk about dose uniformity, I talked about that 1.6. So we have our 25 to 40 kilogray processing window, for example. Our maximum dose is going to be the maximum amount of radiation we validated our product to receive and demonstrated that it is functional throughout its defined lifetime. So that means its packaging is going to stay intact and remain as a sterile barrier throughout its life. That means the product is going to remain functional throughout its life. So if it's an implant, that becomes very important because the life of that product might become the life of that person. So that could be on the order of 80 to 100 years, for example. So when we talk about max dose, we want to make sure that we have something higher than our processing window because product is normally going to receive 25 to 40 kilogray. We want to make sure our maximum dose is something higher than that so that we have a little bit of buffer. That way, if, for example, something is dosed incorrectly, we can add additional radiation and get it dosed properly. So we hit our minimum sterilization dose. If we fail a dose audit, for example, which we'll talk about dose audits when we validate, but if we fail a dose audit, we have what is known as dose augmentation, which is we essentially dose the product with a little bit more radiation to make sure it's sterile. We want to have that maximum dose somewhere higher so that we can receive that little bit more radiation and the product remain functional. So guidance is provided within the ISO standards when it comes to establishing kind of your dose ranges and your maximum dose. Kind of the key to consider is that your product is going to be validated for sterilization. If, for example, at 25 kilogray, you're going to have your processing window that's going to be 25 to 40. Pretty much all of your other validation activities are going to be at that max dose, say 45 kilogray, 50 kilogray. So your packaging validation, your biocompatibility, your toxicology is applicable, is going to be done at that maximum dose to demonstrate and ensure that the product can withstand that much radiation and remain functional. So let's talk about that dose map because that gives us our dose uniformity ratio and our delivered dose. So just like when we map an oven to find our hot spots and cold spots, that's literally what a dose map is we load in a number of dosimeters. So you can kind of see in this pattern here, every square is a dosimeter. And we're going to load up all these dosimeters and we do it three-dimensionally. So we're going to place the dosimeters throughout the load and we're going to see essentially where's our highs and where's our lows. So things that can affect our dose map are going to be things such as carton dimensions, shipping carton weight, because that's going to be kind of what determines our density. So how heterogeneous, Words are hard sometimes, especially when you've been talking heterogeneity and homogeneous. So basically, how is the density distributed throughout this product? If I have a really high density product, just like in an oven, if I have a really high density zone, that's going to take longer to have a temperature change. Well, kind of similar with gamma. If I, or E-beam or X-ray actually, so any radiation source, if I have a higher density area, that's going to take longer to absorb more dose. So that essentially becomes a cold spot. If I have an area of low dose, that might become kind of my hot spot. So when I'm also doing that, temperature can affect things as well. So I'm going to have potentially things such as ice or dry ice going through the chamber. So if I'm doing that, again, the temperature is actually going to affect my dose delivered. So that can be a factor as well. So when we do our dose map, what we're essentially doing is finding where's our hot spot, where's our cold spot, and therefore can this product go through our chamber? Meaning, can we consistently bake this in our oven? So not every oven is created equal, not every irradiator is created equal, and some products are going to be fine in one oven. They're not going to be okay in another oven. Similarly, some products are going to be fine in one irradiator. They may not do as well as another irradiator. And that's really where the dose map comes in, is figuring out what our high and low doses are. So let's take a look kind of at a gamma dose map. So in our example, we have a low density and fairly homogeneous product. So we actually have this specimen cup. And it may not seem the most homogeneous because I have a big air void, for example, in here, followed and surrounded by plastic. But for example, if I'm hitting it with an E-beam from the side, whether I'm hitting this bit of plastic or this bit of plastic, excuse me, ultimately I have about the same amount of material, even though I have a varying amount of space. I do have a bit higher density area here at the cap, but overall, over the course of a whole load, this actually does tend to be a fairly homogeneous product, and it has a lot of air to it, so it does tend to be fairly low density. So I'm going to load that product into my carrier. So I'm going to place dosimeters not just in the individual box in 3 dimensions, but actually throughout this entire carrier. And I'm going to see where's my highs and where's my lows, and I'm going to see what my dose uniformity is. So I'm going to plot that out. I'm going to say I have my low, and then I'm going to plot all my various points until I get to my high. And that's going to give me my dose uniformity ratio. And that's all dose uniformity ratio is. Like I said, it's basically the ratio between your low and your high. So in this particular example, I get my normal 1.6 multiplier. So I have a specified dose range of 25 to 40 kilogray. My 1.6 multiplier, I'm able to do that dose just fine. So this is what it tends to look like. We're not going to spend a whole lot of time on this slide, but you may have seen what a dose map looks like. So you'll see the position of the dosimeter. We do the dosimeters usually in triplicates. So we have run 1, 2, and 3. So we have what position? We have our average here, which is our low. We have this position here, which is our average for our high, and we're going to use those in order to get our dose uniformity ratio. Simple as that. And then based on your product and what your dose range is, so what your minimum dose is to be sterile and what your maximum dose is that's still able to remain functional, we're going to see, does that fit into our radiation cycle, meaning can we fit this essentially into the oven? So if we have a product that can't fit because its dose uniformity ratio is too wide, for example, then really we only have 3 options. Number 1 is we can see if a different irradiator can get a higher dose uniformity ratio. So we can essentially change what oven we're baking it in. The second option is we can try and validate to a lower sterilization dose. So maybe we pick 25 kilogray, but we actually have quite a lot less bioburden. We can try to validate to a lower sterilization dose to kind of give us a little bit more range and a little more room to work with. Or let's say we only validated our max dose to 50 kilogray, we can try increasing that to an even higher dose. Now, of course, there's trade-offs with all of these. If I have an irradiator that's just down the road, but it's not process capable, and an irradiator 2 states over is process capable, well, now I've picked up a whole lot of shipping costs and a lot of shipping logistics that go with that. So that may not be the best option. So if I try lowering my dose, but my bioburden is too high, then I need to implement stuff on my end, such as tighter clean rooms, tighter controls, maybe even a cleaning process, which I now have to validate. All of that is going to add up over time into increased production costs. If I try to increase my maximum dose, I may be causing effects to my product, which could potentially shorten my shelf life. And potentially, I'm having to do additional validation activities, such as my packaging and shelf life validation. I might need to do a new one. My biocompatibility, I may need to reassess that, and I may find that it's no longer biocompatible. So each one of those kind of has its own advantages and disadvantages. So depending on if I can't hit my dose uniformity ratio, I do have generally those three options, but which one is going to be best is going to depend a lot on logistics and what's going to work best for that product in your situation. So some of our dose mapping takeaways. So first, we'll talk about photons, so our gamma and X-ray. So for many materials, dose mapping is based on the dose distribution, which is just a standard grid. So we can tell the variability from position to position. So that also, because of just how consistent it is, does allow us to make some basic assumptions about how heterogeneous or homogeneous the product needs to be. So larger masses tend to include products such as ophthalmic implants, orthopedic implants. So if I have a great big knee implant or a great big hip implant, that's going to be very dense. That's going to affect things much differently than if I just have something that is made out of even just, for example, 3D printed implants, which have a whole lot of void space. There's going to be a really big difference there. So kind of some considerations there for our photon. And then for our e-beam, there is no standard grid approach. So a lot of times your dose map is going to be custom every single time based on your product and your configuration. So again, this is also where think trays, not pouches, think orientation, not just into the tray. So even low density, fairly homogeneous polymers tend to have fairly large dose gradients when it comes to electron beam. So just a small little change in density kind of can mean the big difference between where my high dose is and where my low dose is. So small differences start to add up, and that's also why you'll start to see very big differences in your dose uniformity ratio. Uh, so kind of some considerations there when it comes to your e-beam consideration. So kind of also with that electron beam, your dose mapping, this is kind of an example of how it's going to be very different. We can't just use a grid approach sometimes, especially if we have kits that have various components, or we even have a mixture of products. So we can't just do a standard grid, for example, like the top all the time, because I may have product where I have this product load where I have a difference in density versus, say, this part of the kit, which is a different part. So a lot of times my dose map actually ends up looking a little bit more like the one on the bottom here. So again, dose map for e-beam does tend to be a lot more involved, and that does make it fairly time consuming and potentially also cost more. So doesn't mean that you shouldn't do e-beam. It just means that we need to be considerate of the packaging, how consistently we can keep the packaging, and then kind of plan accordingly for our dosimetry and our validation activities. Give yourself some extra time if you're planning on validating via e-beam so that we have the necessary time for a dose map. So kind of our takeaways, as I mentioned, with E-beam, there is no standard dose map. It is going to vary quite a bit based on your product, your configuration, your kit. And one other thing to kind of keep in mind is we may even have to open up some of your packaging in order to place those dosimeters. If I have a tray and I need have a tray that has a low density area and a high density area, I may need to place dosimeters in that tray. That potentially means pulling off the Tyvek top, place the dosimeters, place the Tyvek back down if it's a Tyvek tray. So just kind of keep in mind some of that with our E-beam is we generally are going to need to do that dose map, and that could also mean we need some dedicated test articles for it. So before we move on, I do want to pause for a moment and see, are there any questions about radiation, gamma, E-beam, X-ray, kind of questions about modality or dose mapping? All right, we'll move on. So let's talk a little bit more about bioburden testing. So since radiation sterilization is a bioburden-based sterilization method, the bioburden plays a much bigger role than it does in some of the others. So as we mentioned, it's the population of viable microorganisms on or in a product. And we'll kind of clarify here since we are talking about sterilization or sterile barrier system. So sometimes we're considering just the sterilization of an individual product. Sometimes that might include everything within the sterile barrier system. So your sterility claim and where the sterility claim is on your sterile barrier and what's being claimed as sterile all kind of need to be considered. So our guiding document for bioburden testing is ISO 11737-1. That was revised in 2018. As we talked about earlier, we are looking at those colony forming units. So those individual colonies are what we're looking at because we don't know, do I have a cell? Do I have a clump of cells? So the question comes up, and I open this up, so feel free to answer if you would like. What do we do with this? If you see a plate that looks like this, what do we do?
Oh my gosh, sorry, I lied. Count the microorganisms?
We hopefully can try and count, but a lot of times when we have a plate like this, we can't even make out individual colonies.
Oh, so this would be considered a spreader, I think, correct?
It might be a spreader. It might be too numerous to count. So sometimes we really don't know. It's what we refer to as confluent growth. So if we can see what we think are individual colonies, we might call this a too numerous to count, TNTC. If it's, for example, just like this particular one where I just have this lawn, it might be a spreader. It might be both. The thing is, really, this is not what we want to see for bioburden testing because this is not something that we can quantify. So the answer is, what do you do with this is we need to do more testing. So one of the first things that we can do, we saw the video, is we can try something such as an auger overlay to see if it's spreading and try and trap these organisms so they don't just spread across the filter. We also, microorganisms like to follow debris. So if there's lots of debris on the filter, again, sometimes an auger overlay can help with that. But an auger overlay can be a two-edged sword. If we've had motile, meaning they can move around microorganisms, we've done auger overlays before, and then the organism basically just goes out from under and spreads across the entire top, not trapped at all. So we can try sometimes what we call full plate auger overlays, where instead of just overlaying a portion, we'll overlay the whole plate. But if this is a TNTC, too numerous to count, then we need to change our testing. So we keep track of our volumes in. You saw us weighing that. We keep track of what we filtered. That's our volume out. And that actually gives us a ratio. We call it our volume-based correction factor. So to test for aerobes and fungals, for example, I might test a third of my fluid for aerobic, a third of my fluid for fungal, and then I have a third of my fluid for my controls. So in a case of a too numerous to count, instead of testing a third of the fluid, I might test 1/10 or even 1/100th of that fluid so that I can try and get counts that are in the countable range. But I generally don't know what my bioburden is going to be ahead of time. We tend to be just as surprised as you. So if I am seeing something like this, chances are you're going to have to send in additional samples, and we are going to have to change and improve the test method so that we can get something that we can actually count. So when we talk about that, let's go the complete opposite direction now. Let's say I have a product with extremely low bioburden. Well, as I just used in the example, I might test a third of my fluid for aerobic, a third of my fluid for fungal, and a third of my fluid for controls. Well, that means I only tested 1/3 of my fluid for any given test. So that sets up a limit of detection. Our volume-based correction factor of 3 becomes a limit of detection, which, and I have some examples, typically is reported out, for example, as less than 3. Well, if I have a product that I need to get a very low dose for, that limit of detection can become problematic. So if I have less than 3 for aerobic, I have less than 3 for fungal, I add those together, I now have less than 6, and yet I've actually seen no microorganisms. So that limit of detection can become problematic. So one of the ways that we can solve that is with a more sensitive test. So the most sensitive test that we have for ISO 11737-1 for bioburden testing is the most probable number test, or MPN test for short. So there is a lot of overlap between the MPN test and the test of sterility. We actually can use the same bacteriostasis fungostasis test in a lot of cases, because what we're going to do is, just like a test of sterility, we're going to take the product and we're going to place it into growth media, and then we're going to score that as growth or no growth. Now, what's key is we are testing 10 samples. So we're going to need at least one of those samples to come out as negative for growth. So what that overall means for a product is you essentially have a nearly sterile product, meaning lacking viable microorganisms to begin with. So that does require a, number one, random distribution of bioburden and exceptionally low bioburden, so that there's little to no bioburden at all. So the formula for the MPN test, and I will point out the formula in the ISO 11737-1 2018 standard is wrong. There is an amendment where it is correct. This is the correct formula for MPN testing. But what it is we take the natural log of the number of samples tested, divide that by the number that are negative for growth. If all are negative, we'll assume one positive in order to make the math work. And then we multiply that by the sample item portion if applicable. So if I test half of a product, I need to account for that. So that would be a sample item portion of, for example, 0.5. So I would take 1 over the SIP to account for that missing half of the sample. But overall, this is our most sensitive test. If you plug it in, if I have 10 samples, my number of negative, if I assume 1 positive for calculation purposes, so I have 9 negative samples and I take the natural log of that, that gives us a bioburden of less than 0.11. So When we're talking a little bit later about some of our very low doses, and if you're familiar with radiation sterilization, something such as VD-Max 15, which has a maximum allowable bioburden of 1.5 CFU, this is kind of the way that we get to those very low bioburdens is we can do most probable number testing in order to get us those very low doses. So on the one end, we have too numerous to count. We're going to have to make the test much less sensitive so that we can get it in the countable range. On the other end, we have the most probable number, which is the most sensitive test that we can do and run. So that brings up the question, bioburden, what is a good bioburden count? And how do we determine what good is? So bioburden, what is a good count? Again, really, it depends. It's going to vary based on your product and what you're doing. If I have a TNTC and I'm routinely having to do a very high factor to get it in the countable range, I may see some that are less than 1,000. That is a very possible number if I'm having to do that high factor, because I might have some product that's nearly TNTC and some product that has not as much growth. So I might have one that could be 1,000, 2,000 CFU. I could have another one that's right next to it that is just less than 1,000. So this would be an example of if I have that very high factor of some possible results. I could have bioburden that is fairly low, such as 35 CFU, less than 10 CFU. So what is good really depends on your product and your sterilization. Now, I did throw one in there that you really shouldn't see on a regular basis, and then I put it front and center. So 0 CFU really shouldn't happen. So when we're talking about raw counts, so just what we're seeing on the plate, I might see a 0. However, all of the bioburden testing that we do has a limit of detection. So our most sensitive is that MPN test. It tends to be for 10 samples 0.11 CFU. So it's very close to 0, but we're not at 0. If I'm doing a extraction, so I'm removing it from the product and I have that liquid in bottles and stuff, I'm probably going to see something more along the lines of a less than 3, for example. I really shouldn't see 0 CFU in my what we refer to as calculated counts. So if you're seeing 0 somewhere on a bioburden report, you should question it. Is this a raw count? If it is a raw count, what is my calculated count? So that you can understand what your true bioburden. 0 CFU really shouldn't be something that is popping up. We should have that limit of detection somewhere. So one of the other things to bring up when we talk about what is a good bioburden count, I have been a study director before, and I have had a sponsor that called me up on a Friday afternoon. It's always Friday afternoon. I don't know why, but that's just the way life works. Called me up on a Friday afternoon, and they were absolutely livid that Nelson Laboratories, and in particular myself, did not call them ahead of time and warn them about their high bioburden. And they were very, very upset about their 35 CFU. And the thing is, for some products and some manufacturers, they would love to have bioburden down at 35 CFU. They're used to seeing stuff more around the lines, for example, of 767 CFU. The thing is, us as the lab, we see the whole range when it comes to bioburden. I've seen products that we'll put it in the MPN test, 10 out of 10 are negative for growth, and that's the bioburden test. It's coming to us essentially with no microorganisms on it. We've also been asked to test a septic starter before, and that required many, many, many serial dilutions and was well in excess of 10 million colony forming units. So when I see something like 35 CFU, that really doesn't trigger anything for us or what we're looking at. So it's very important that you set alert and action levels that matter to you. And we, the laboratory, can't really interpret what is and isn't a good bioburden because it does depend so much. So why did I not call them and warn them about their 35 CFU? Because to me, it's just a number. I really don't know what its purpose is, what the intent is behind it. So what is a good bioburden? Again, it depends. So that's also where it's important to set meaningful alert and action levels for your product. So the question then comes, what do I do with high bioburden? So the first thing we do is we investigate the process and the raw materials. So the second is have knowledgeable people involved. Next, identify the microorganisms. This can tell you a lot about where your high bioburden is coming from. If I'm going back to kind of our earlier slides, if I have gram negative, I have a good indication that I need to go look at my water systems. If I have positive cocci, I need to start looking at my personnel. Are they wearing their PPE properly? Are they trained properly? And then what do? I fix it. So I have a story when it comes to knowledgeable personnel and why they are key and critical. So we had a manufacturer that they had a dose audit failure. So they were doing their routine dose audit and they had too many positive tests of sterility. And when we also got looking back through it, we noticed that they had fairly high bioburden. So they did what we do recommend, which is they identified the microorganisms. So when we identified those microorganisms, we saw quite a lot of Pseudomonas. So with that, Pseudomonas is a gram negative. So the very first question we ask is, well, where's your water at in your process? And let's take a look at your water. And the response was, oh, there is no water in our process. We do not have water in our process. Okay, well, you have gram negative organisms. They have to be coming in from somewhere. So we started looking into it and we did what we refer to as investigational testing. So we took their device and we broke it out into components and we tested the individual components to see which components or potentially have this gram negative organism and which ones don't, so that we can try and narrow it down. Well, what we found is all of the components had this gram negative organism. And we sent it again for identification, and it came back as the same organism. It was a gram negative organism. So we again asked, well, there's got to be water in your process. And they were again insistent. So they start going to their suppliers and seeing where their suppliers have water in their process. And their suppliers come back to them and their suppliers indicate, we don't have water in our process. This is just molded, packaged, sent to you. There's no water in our process. So I was a bit confused. So I asked for a diagram of their process. I'm a very visual person. So I asked them, hey, I would like to understand your process. I'd like to understand your production. Can you chart it out for me? And then I can look at the individual steps, how this is being assembled, and we can kind of take a look and see maybe where some additional places to investigate. And the individual says, well, sure, I can do that. I don't have visibility on that, so it'll take us a day or two to chart that out. I need to get a few people involved. A couple days later, email comes to me. It's the chart. I open up the chart, and right there at the very end of the entire process is rinse the product with water. So I go back to my individual who sent me the email and I've been working with, and I was like, hey, did you take a look at the chart before you sent it to me? And he's like, well, I don't really know the process, so no, I didn't look at it. And I was like, well, it literally says right at the end of your production when it's all assembled, which explains why all of the components we tested had the organism, it says rinse with water. And he's like, no, that can't be right. Goes back to his team, and they had had an issue with their product. They had had an issue with residuals. They weren't really specific to me on what the particular cause was, but the decision was made to rinse the product with water. And they figured that that shouldn't be an issue because it's water. There shouldn't be a residuals problem. Well, that rinse, they didn't have the knowledgeable people involved on what they're doing and why. They didn't understand the microbiology aspects. They were really only concerned about the residual aspects. And the person that I was working with did not know that that step had been introduced as part of a change to the product and production. So point of that and the moral of the story is make sure you have people involved throughout the investigation that understand what is happening with that product and why that matters so that you don't have a whole lot of additional testing and then me asking at the end, so here in your chart it says you have water even though you've been very insistent for the last several weeks that there's no water. Nobody wants to have that experience. Nobody wants to spend the money on that testing. So make sure that the right people that know what's happening with the actual product, not just what's supposed to happen with the product, but what's actually happening with the product is involved in that investigation. So one of the next common questions we get about bioburden is, what is a spike and what do we do with it? So there really is no standardized approach to what a bioburden spike is. We are working at the ISO standards level to better define a spike. There currently is not a standardized approach, but often what we use in the industry is, for some example, something that's 2x the average. Another way that people tend to do it is if it visually looks like a spike, such as is over here on the right, then chances are that's a spike. But a good one is that 2 times the average. So can I discount that spike as an outlier? And this is very important. With bioburden testing, there is no such thing in bioburden data as an outlier. This spike is likely an indication of an infrequent problem. So let's go back to the fiber bundle example. Not every single sample was having issues with that fiber bundle getting its sheath put on. So some of those probably just looked like this. And then we have a spike where somebody had to lick the fiber bundle in order to get the sheath on, and that leads to our spike. So generally speaking, when we see spikes, those are an indication of an infrequent problem, and we want to see what that problem potentially is. So we want to take a look and investigate it. Yes, Scott.
Hi, Bryce. I missed the last hour of the session while I was on a different call, so maybe you already covered this, but it seems to me that the data should be transformed before analysis. So mathematically transformed using like maybe the log normal function. Do you have any thoughts on transformation of data before analysis?
So the ISO standard does, in the annex, give some background on statistical options and even statistical diagramming, such as fishbone and things like that. As I kind of indicate here, there is no standardized approach. Generally, people don't do a mathematical transformation such as a log. A lot of times it's looking at averages such as 2 times the average and standard deviations. So a lot of times you're going to set alert and action levels, and those alert and action levels are going to be based on your historical data. You generally using standard deviations tends to be a common approach. There are times where we will sometimes look at things logarithmic. So sterilization tends to be logarithmic, but generally speaking, for our bioburden trending, we generally don't do log transformation.
Thank you.
So let's talk for a minute about recovery. But Bryce, we just talked about recovery. Why are we talking about recovery efficiency some more? Well, the answer is because every single auditor is going to look at your recovery efficiency. So why is it important? Because your entire dose setting for radiation sterilization often flows through that recovery efficiency. Radiation is bioburden based. We look at and establish our doses based on that bioburden, and we generally don't have that bioburden estimate without that recovery efficiency. So it's a measure of the ability of a specific technique to remove the microorganisms. So overall, we're assessing the entire system. So I might have a product, for example, here in this bottle, and I might do orbital shaking, or I might do a combination. I might do orbital shaking in sonication together in order to try and remove those microorganisms. But overall, I'm assessing that system and its ability to get those microorganisms off that product into that solution and detected for our test. And why is it important? Because every auditor is going to look at it, because that recovery efficiency, talking about mathematical transformations, does transform the data. If I have a recovery efficiency of 95%, that's going to affect the data a whole lot different than if I have a recovery efficiency of 25%, and that's going to affect how I set the dose. So they're going to look at your bioburden. They're going to look at how your dose is set, because that's your entire sterilization validation is that dose setting. And that means they're going to look at your recovery efficiency, because all of that dose setting runs through that recovery efficiency. So let's take a little bit deeper dive beyond just what a recovery efficiency is and kind of how to look at and interpret some of that data. So when I have a repetitive recovery efficiency, I'm going to have a number of samples. I'm not just going to look at one statistical data point. So for example, here I have 5 samples that I'm extracting, and then I'm going to extract it, like we mentioned, multiple times. So I'm going to have my first, second, third, fourth extraction, just like we kind of showed earlier in that I'm going to do that repetition. Well, this is what it actually looks like numbers wise. Is I have my bioburden in my first extraction, and then I have my subsequent extractions. Now, one of the reasons we don't call it an exhaustive recovery efficiency anymore is, like I said, we really don't know where exhaustion is. It's more so a repetition, because this one, for example, I still have a 2 here. I may not have potentially hit exhaustion. So the true term is a repetitive recovery efficiency. So how does this look when we actually do the math, and how are the values calculated? So what it is it is the first extraction divided by the sum of all extractions. So we'll use this first column here. So we have 67 CFU in our first rinse divided by the sum of all of our rinses. So this is essentially our total bioburden. So 67, 15 plus 7, that gives us 0.753, which is a 75.3% recovery efficiency. So it's the percentage of the total bioburden that we're essentially getting off in that very first extraction, because that one extraction is how we're going to test basically the majority of the product. So that gives us our recovery efficiency. That's also called a correction factor or a correction percentage, because it is correcting what we're extracting to determine what the true bioburden of the product is. So if we do the math for all of them, we can kind of look through and we can see we have 75, 73, 86, 76, 64, and this is fairly common, what we will see for repetitive recovery efficiency. So I'm going to again open it up, and you can unmute your microphones. What do you think would happen? What should we do if I'm just seeing the same numbers continuing down? If I'm seeing 67, 67, 67, 67, what could be causing that, and what should we potentially do? Any ideas? No brave souls? So it is something that we do see sometimes, is we will actually see the bioburden just stay there. So that may mean that the product is falling apart and we're actually shedding more and more and more bioburden. We might not be doing a very good extraction, so we might try extracting the product differently. So if the product is falling apart over time, we may want to have an extraction that is longer. So our extraction methods, for example, if we go back to our previous slides, we have orbital shaking, reciprocal, manual, stomaching, sonication. Manual shaking is one of our defaults because it is a very vigorous extraction. It gets the extraction fluid all over the place. It's a very vigorous extraction, but it's also very short. We extract approximately 100 times in a 12-inch path. Well, you can imagine if you're manually shaking a bottle 100 times, that takes roughly 1 minute. Whereas if we do reciprocal shaking, if we do orbital shaking, some of our typical extraction times are 15 minutes. So reciprocal shaking may not be as vigorous of an extraction in some cases, but it does allow for additional contact time, and that may allow for the product to extract differently and potentially better. So if I'm seeing a product that's starting to break down, if it's breaking down over time, a longer extraction time may lead to a better and more representative extraction. We've also seen instances where the recovery efficiency results actually inverse. So, for example, we've seen zeros towards the start, and we've seen high recovery efficiencies at the end. That's usually an indication that we have something like a coating, and that coating is breaking down and there's bioburden under that coating. So as the coating breaks down, we're recovering more and more bioburden from underneath it. So that would potentially be another situation where we might want to increase our testing time or increase how we're extracting the product. So inoculated recovery efficiency, the math really works out quite simply. So it's the amount of inoculum we recover from the product divided by the inoculum we put on the product. So we are going to inoculate onto the product. So that's kind of one of the first things is potentially we can actually lose inoculum. Sometimes we have very fine things. This is actually a BI preparation, but it works the same way. Is we have very fine wires, very fine threads, lumens, things like that. And we have physical limitations to how small we can make our inoculum that we're putting on. So if, for example, this drop falls, we've essentially lost that from off the product and we're not going to be able to account for it. So we potentially have some issues when it comes to inoculated recovery efficiency. One of the first is that, like I said, we can lose inoculum. The other thing is we do have a spore suspension, and even though it's in spore form, we are potentially stressing those microorganisms. So we may have die-off, for example. But inoculated recovery efficiency, it is our modeled approach where we are going to inoculate onto the product. To know what we inoculated on, we generally do 3 control plates so that we can average them out in triplicate. And then we're going to see what we can remove off. And again, we're generally going to do multiples of that so that we can kind of see what an average is. We talked a little bit about why we would use one over another. And generally speaking, if I have product bioburden, then I want to do a repetitive. If I don't have product bioburden, then I want to do an inoculated. This gives us a little bit more guidance from the standard on what that actually looks like. So generally speaking, it talks about if I have 100 to 1,000 CFU or higher, then I might want to be able to do a repetitive. If I have, for example, 10 CFU or less, then I probably don't want to do a repetitive. That's when I'd probably be better off with this inoculated approach. Also, it can vary depending on the product itself. If I have a product that is falling apart, such as a paper backer card that I need to test and I need to know the recovery efficiency, well, that's going to dissolve over time. And if I do an inoculated recovery efficiency, I can see what that first extraction is and what percentage I'm getting off. If I'm doing a repetitive recovery efficiency, probably by the time I get to my 4th repetition, I don't have a paper backer card anymore. I have a pile of paper pulp. So that might be a situation where the nature of the product itself is actually dictating me to do an inoculated recovery efficiency. So then the question comes up, what is a good recovery efficiency? Well, the main criteria is it consistent? So this is very important to remember and keep track of. So in previous iterations of the ISO 11737-1 standard, it mentioned in the informative, not normative, the informative annex that if you don't have a 50% recovery efficiency, you should consider improving the method. 50% recovery efficiency has never been a requirement of the ISO standard, but it was often being interpreted as a requirement. So that's one of the reasons it was removed and is not in the current iteration of the ISO 11737-1 standard. Instead, the main criteria for what is a good recovery efficiency is actually consistency. So really this gets into precision versus accuracy. And what I want to do is I want to have a bioburden estimate that is both precise and accurate. But part of the way I do that is with my recovery efficiency. And is it consistent? If my recovery efficiency is not consistent, I may have a recovery of 25%, 50%, 75%. If I average those together, I have a 50% recovery efficiency. And that might look good, that might seem good, but the thing is, a third of the time, I'm only getting 25% of my bioburden off, and a third of the time, I'm getting 75% off. My extraction is extremely inconsistent across it, and therefore, I'm not able to do good repetition. I'm not able to get consistent results with that test method. So again, consistency of the recovery efficiency really is the more important, and it is the main criteria of the standard, not that arbitrary 50%. I can have a terribly inconsistent recovery efficiency and still hit that arbitrary 50%. It doesn't mean it's a good recovery efficiency just because I'm at 50%. Now, that being said, if I am below 50% and I have a consistent recovery efficiency, that is good and can be acceptable. However, I still might want to consider improvements to the method in order to try and get a higher recovery efficiency. So it's kind of a it depends situation. 50% though is not the do all end all. Consistency is not the do all end all. Consistency is the main one that we want to consider. But if I have an arbitrarily low recovery efficiency, if I have, for example, just 5%, I can consistently have 5%, 5%, 5%, but that's probably still not the most representative as I'm not accounting for my other 95% of my bioburden. So ideally, we want both consistent and a high percentage, but we kind of want to have some guidance. So there is quite a bit of wording behind this in the ISO 11737-1 standard in Annex C. That's the informative annex entirely on recovery efficiency. Generally speaking, it does give some examples. For example, if it's a 25%. Need to mute someone real quick. So if we have a recovery efficiency of 25% and it's very consistent, generally that's probably going to be okay because we are still accounting for a fourth of our bioburden. If I have a 75% recovery efficiency and it's inconsistent, that's probably less good. It is a bit arbitrary, and that is where having kind of a knowledgeable person involved can really matter, is because it also is going to depend based on our product and again, what we're trying to do. So I actually have a working example based on your data that was provided to me. So let's take a look at that. So first, let's take a look at our bioburden. So this is from a dose audit. So is there anything in particular in this bioburden that stands out to anyone? Feel free to raise hand or unmute if you see it. Yes, Garrett.
Got a spore spreader, and there seems to be some, relatively high values, but then mostly really low values.
Yeah. So in this one, I have the A here. That's an indication that I have a spreader. Now, overall, if this was my study and I'm doing interpretation of data, I'm not the most worried about this because overall my data is fairly consistent. I am seeing a 43. This 32 is potentially being underestimated. It could be quite a bit higher potentially, but I'm probably not the most worried. One of the next things I'd look at is, okay, I have my recovery efficiency here. So maybe let's kind of look at that first. So let's take a look. We have a spreader. Chances are if I have a spreader, let's see, do I consistently have spreaders across my product? Is this something I need to worry about? Is it potentially affecting my sterilization if it is underestimated? Something such as an identification may be warranted depending on your level of control. This is one that it definitely should get your attention, not necessarily action, but definitely your attention and consideration. So the next thing, like I said, let's take a look at the recovery efficiency. So the recovery efficiency that was applied is historical data. So I went ahead, pulled up the final report for that, and this is our, we do say exhaustive, our repetitive recovery efficiency that was performed. So it's kind of there. It basically has its own whole thing is our recovery efficiency itself has an indication of a spreading microorganism. And when we're talking about consistency, this isn't the greatest on that. So I do have two results that are fairly consistent. I'm right at 60% recovery efficiency area. But then I have this one that's 33% recovery efficiency, and it's being affected by spreading microorganisms. So this might be an indication of one where we look back, we take a look at this one right here, and we look at our recovery efficiency and we go, well, is that really representative? Because this is really pulling that average down, especially over the course of just 3 samples. So additional testing to see what our consistency really is may be warranted. And with that additional testing, maybe taking action in order to minimize our spreading, perhaps something such as a auger overlay in order to try and trap those microorganisms. But most certainly probably along the lines of gathering additional data points so that I have an additional set of statistical data to base my consistency off. Yes, Scott.
That all makes sense to me, but if we're going to have a recovery efficiency that is off, wouldn't we prefer it to be on the low side rather than the high side?
Potentially, it depends on how we're interpreting the data, though. So if I'm setting my dose, which we'll get to a little bit later on, I'm actually biasing myself towards passing, and an auditing body is going to look at that. So there actually is wording in the standard about overestimation of bioburden and how it can affect our validation. So sometimes a recovery efficiency being low might be seen as a worst case when it comes to dose setting, and I'll make sure that we address this when we actually do an example dose setting, is we actually may be biasing ourselves higher and actually creating less of a challenge, which could be seen as problematic for a regulatory body. So that is a good question, and we'll get to it.
All right. Yeah, I'd be interested in seeing that because I'm having a hard time making that leap today with what I know. So
Yeah.
I'll stay tuned for that one. And then another related question. And this leverages some of your earlier discussion earlier in the morning. Bioburden is more important in dose setting sterilization, like gamma, than
Yep.
it is in ETO. So should we place a higher level of scrutiny when we are evaluating bioburden reports when we are working with gamma product versus EO product?
The short answer is yes, very much. So with EO, I have the most resistant organism. I have 1 million CFU of it, and it's in the most challenging to sterilize location. Do I care about my bioburden and ensuring it's controlled? Yes. But generally speaking, there has to be a lot that goes wrong for my bioburden to start becoming similar and comparable to that biological indicator. I have to have a considerable increase in my bioburden. And that's also something that Tony will talk about a little bit. But yes, my bioburden for a bioburden-based method, such as radiation, I need to look at it and give it considerably more scrutiny than I do for my EO and my overkill-based methods. And this is also probably something that you'll actually even see in your testing data. So I'm actually going to go to the next slide real quick because it's an example. But in your bioburden testing data for radiation, for example, we're generally testing 10 samples. For a dose audit, that is what is prescribed by the standard. For something such as ethylene oxide, generally you're not testing 10 samples. You're testing something more along the lines of like 3 samples. And that is kind of indicative of, yes, the bioburden is just that much more important. So we want the bigger statistical model for a bioburden-based sterilization.
Yeah, that makes sense because really some of these discussions become pretty academic when you're when you when you're comparing small changes in an of bioburden in an EO modality.
Yes. So to kind of put that into perspective and kind of for the group, when we talk about setting like alert and action levels, how we set those is going to vary based on our sterilization. And for something like EO sterilization, 150 CFU, 200 CFU, 250 CFU, those sound like big changes, but in the aspects of something like EO, they're actually all in the same log. They're in what we call log 100. And microbiologically speaking, for something such as EO, they're pretty much all the same because whether it's 150 or 250, at the scales I'm working with EO, it, for lack of a better term, really doesn't matter that much. It's all the same log. So here's our next working example from another dose audit that we have. So with this one, kind of things that very much are kind of become apparent is we do have what we would consider a spike. So for example, we have our average, it's 48.5 CFU, that does include that. But when we look through overall, the highest count we're really seeing is that 45. So when we talk about something being 2 times the average, I can multiply 48.5 by 2. I'm still not getting up to 219. So this is an example in the data set of what a spike would potentially look like is, yes, I have this spike here. It's 2 times the average. So that's probably something we should take a look at and see, again, do we have an indication of an infrequent occurrence of an issue? So am I seeing something that is causing a high bioburden once in a while? Now, this doesn't necessarily mean that I have an issue with my product and sterilization, which is why a dose audit is 2 parts. So when we talk about radiation and when we talk about dose audits, there's the bioburden and there's the test of sterility. If the bioburden is high, that's potentially kind of concerning and we should investigate it, and it can affect sterilization. But we then have that verification dose experiment, that test of sterility, that is going to directly challenge it. And if that fails, then we definitely have a problem. If that passes, well, sterilization's okay. Sterilization's accepted. Let's take a look at the bioburden and see what we need to do to get it back under control before it's no longer okay. So we do have this one here that is a spike that is showing up in the actual data that I was shown. So I thought it was good to show. So this particular one, I pulled up its historical recovery efficiency. Nothing actually interesting or unusual there, so we won't go into that one for an example. So questions about bioburden and recovery efficiency so far? Any additional questions at this time? Yes, Nicole.
If you go back a couple of slides, Bryce, for the recovery efficiency here where it was 52%, and then you kind of dug into the details, how often should we be looking at the recovery efficiency and considering performing like another assessment?
So if it's something that just hasn't been done, then now's a good time to do it. Generally, that's something you want to take a look at during the validation. So for example, Nelson Labs, if we're doing a validation, we will send a bioburden preliminary report prior to dose setting and doing that. So when you're doing the validation is really the time to take a look and assess and kind of see, is this recovery efficiency okay? Is there something additional or something else I should do? This particular one, for example, as I mentioned, we do have this lower result. It is being affected by a spreader. There are things we can do, such as getting a bigger statistical base, but even just if we're choosing not to take action, this is during the validation is the point when you should write and have some rationale about why this recovery efficiency is okay. But generally speaking, you're going to do that once. You're going to do that during the validation, for example. If it hasn't been done during the validation, now's the time to go back and look. But generally, you're going to do that once, and that's going to be your assessment. And you're really not going to assess it again unless there's a change to the product. Because if the product stays the same and our test method stays the same, which our test method is set by the CSS, so it should remain consistent. So as long as the product is staying the same too, it's not changing materials, it's not changing suppliers, then the recovery efficiency shouldn't change either. But that should be part of your change control is if I am making a change to a material, if I am making a change to a supplier, that might affect the recovery efficiency. And that might be a good time to repeat the recovery efficiency and compare to your data. Did it affect the recovery efficiency? Did it not affect the recovery efficiency? And then kind of proceed forward from there. But generally, to kind of answer your question, quick summation, assess it during the validation and then assess it again if there are changes to the product.
Okay.
So also with that, because that brings up a common question, is we do have the bioburden method suitability, which is our inhibition check. And generally that works fairly similar, is we're going to test and we're going to demonstrate that the product is not inhibitory as tested. Generally speaking, that initial kind of check is going to be sufficient. But if there is a change again to the product, raw material, supplier, something like that, that may be a good time to also reassess that method suitability and make sure that we don't have inhibition. We might have switched to a supply from one supplier to another. It might be the same material, but let's say the new supplier uses a different release agent. That release agent, for all we know, may be inhibitory. That can affect the overall product inhibition. So kind of similar situation when it comes to the method suitability and inhibition. So we'll go into sterility assurance level. I know some of you are coming in, so it's a good thing we have a bit of a repeat, but kind of just some of the nomenclature behind it. So 10 to the minus 6, that's a 1 in 1 million chance of an organism surviving. 10 to the minus 5, that's 1 in 100,000. 1 in 10,000, 1 in 1,000, 1 in 100, 1 in 10. That's kind of how we progress through sterility assurance level. So it is expressed as 10 to the minus n, and we are talking about that probability of a viable organism present on a product after sterilization. So for verification dosing, our validations break down into VDMAX and method 1, and our sterility assurance level kind of breaks down accordingly. So 10 samples, that's our 10 to the minus 1 SAL. 100 samples, that's our 10 to the minus 2 SAL. So VDMAX is our 10 to the 1, method 1 is our 10 to the minus 2. And if you're familiar with doing radiation testing, if you've been reading dose audits or things like that, this will probably become familiar because we test, for example, 10 samples for sterility or 100 samples for sterility. And that's actually why and how this is set is we're testing that sterility assurance level, and that is setting how many samples. So the verification dose, a good way to think of it is similar to a half cycle or a fractional cycle for EO. We're basically not able to test the sterilization dose of 10 to the minus 6. So what we're doing is testing a verification dose that applies to one of those sterility assurance levels. So kind of similar in aspect in that case to a half cycle or fractional cycle. So our visual representation, we have 0. That's kind of where we want, no viable microorganisms. And then we don't just want no viable microorganisms, we want statistically to have less than 1 in 1 million. So we have our baseline here, and VD max 25, for example, we start and we have a limit of 1,000 CFU. We're trying to get down to 25 kilogray. So we have kind of our verification dose, which, for example, is kind of going to be somewhere around here. Now, you'll notice that our verification dose, if you've ever gone to the table, is going to vary some. That's because we're not just going to set the dose based on we have 1,000 CFU and we test here. Our actual bioburden is going to change and vary, and that's actually going to change where we're at as far as our verification dose on this line. So as that moves around, that's going to change our verification dose. But again, just want to reiterate, we don't ever test product that's at the 10 to the minus 6. That represents a 1 in a million chance. You're not testing the product, you're testing the laboratory. So let's talk about how we use the bioburden counts and how we do the validation. So for VDMAX in method 1, verification dose is determined, as we said, by a table. So we use the bioburden that's been adjusted by the recovery efficiency. That's what we refer to as the bioburden estimate. And we're going to go to that table. We're going to see what our bioburden estimate is and what dose correlates to that. So for VDMAX, we have each sterilization dose actually has its own table. So for VDMAX, it goes up in tiers. The way I like to think of it is it's kind of like a stepped approach. So we start at VDMAX 15, and then we go up in 2.5 kilogray increments all the way up to VDMAX 35. So there's 15, 17.5, 20, 22.5, so on and so forth. Method 1 is more like a ramp. Each bioburden count has its own sterilization dose. So as bioburden increases, sterilization dose increases. So let's take a look at the VDMAX table itself, and we can actually see this. So what we have is here in this center column, we have our sterilization dose. So that's up here. That's the table that we're picking for VDMAX, is we're going to sterilize at 25 kilogray. So then we're going to take our bioburden estimate. Let's say it's 110 colony forming units. That's our bioburden estimate for the product. That's going to give us our verification dose. So that's in this case going to be 9 kilogray. So that is basically how we do it, is we have this lookup table, we get the bioburden, we look up what the bioburden estimate is compared to our table, that gives us our verification dose, and then we're going to send product off to receive that verification dose. So let's do the same thing for a method 1. So in this case, you'll notice that we have 3 separate columns. So we have 10 to the minus 2, 3, 4, 5, and 6. So this is one of the advantages of method 1, is we are able to use some of those alternative sterility assurance levels if we need to. VDMAX 25 for our previous example, that's it. 10 to the minus 6 is your sterility assurance level. There is no other alternative sterility assurance levels. Method 1, that gives us our alternative sterility assurance levels. And you'll also notice as bioburden increases, our sterilization dose also increases. So if we use our same 110 for our bioburden. Then what we're going to do is we're going to pull our sterilization dose from the 10 to the minus 6 column, and we're going to pull our verification dose from the 10 to the minus 2 column. So for this example, our verification dose is going to be 8.1 kilogray, and our sterilization dose is going to be 21.3 kilogray. So this is important to remember. So for our previous one at 110 CFU, our bioburden estimate, we had a sterilization dose of 25 kilogray. For method 1, we have a sterilization dose of 21.3 kilogray. So that's one of the other options with method 1 is if we're trying to get the dose down, if we're trying to get our radiation exposure down, this is one of the ways that we can do it, is instead of doing VD max, we can do method 1 and we can try and get our sterilization dose down by correlating it closer to our bioburden. Now, the verification dose does not exactly match up because VD max, our verification dose is a 10 to the minus 1 SAL, so we're testing 10 samples. For method 1, our verification dose is a 10 to the minus 2 SAL, so we're testing 100 samples. So that's part of the trade-off is we are testing 100 samples, so 10 times more samples for our test of sterility compared to VD max in order to get that lower dose. So that is a bit of a trade-off there. So once the product, we've determined the dose, we've set that dose based on that bioburden estimate. And again, I want to reiterate that bioburden estimate includes the recovery efficiency, which is why they're going to include that recovery. So if I kind of come back, I'm going to kind of clear the screen a little bit. So I'm going to do it for both VD max and method 1. If my recovery efficiency is low, so let's say I have, and I'm going to make the math very simple for us. So if I have a bioburden count of 100 and I have a bioburden estimate, if I have a recovery efficiency that's high, I'm going to make this really easy and just say that it's like 95%. That gives us a bioburden estimate that's going to be pretty close to 100. So I get basically a dose of 9-ish kilogray. If I start overestimating my bioburden, in the case of VD max, something interesting happens, and this is worth pointing out since we're here, is up to 80 CFU, as my bioburden increases, my verification dose increases. So if I'm overestimating my bioburden, I'm actually biasing myself towards a higher verification dose and therefore less of a challenge to passing my sterility. But that applies up to a point of this 80 CFU, then my dose actually starts going down. So the way the table works is sometimes I'm actually making things worse for myself if I overestimate the bioburden. Sometimes I'm biasing myself towards passing. So with that recovery efficiency, it's not always best to use the lower recovery efficiency because that could potentially be seen as giving yourself a higher verification dose than you would otherwise have. This becomes even more pronounced kind of on method 1, where just as bioburden increases, my verification and therefore sterilization dose increase. So if I have a low recovery efficiency, I'm actually giving myself both a higher verification dose and I'm forcing myself to have a higher sterilization dose. So there is potential there that I am potentially affecting kind of my dose setting by what I think is making it a worst case, actually not being a worst case, or causing my sterilization dose to be higher than it really needs to be. So with my dose set, then what we're going to do is we're going to expose that dose and do our sterility testing. So again, radiation is a range. I have hot spots and cold spots, and that is applicable even when I do my verification dosing. So generally, we are allowed a 10% variation. So if my verification dose, for example, on VD max is that 9 kilogray, then I'm allowed 9 kilogray plus or minus 10%. So I'm allowed 9 kilogray minus 0.9, and I'm allowed 9 kilogray plus 0.9. So I'm at 8.1 to 9.9 kilogray is my range that I need to dose in. Then I'm going to expose that for my sterility testing. So the proper term, as we've mentioned before, is a test of sterility. And I do want to point out that the sterility standard, just like the bioburden standard, did revise relatively recently in 2019. But generally for the ISO 11737-2, it is considered understood as having received a fractional or sublethal cycle. Again, this is not intended for fully sterilized product. This is intended for stuff that's been fractionally dosed or fractional cycle. So one of the reasons I have the star here is to remind myself that it is the 2019 standard, and we do have a few things that we need to talk about that have kind of changed over time and ensure that you're aware of. So one of those is we talk about sterility scoring, and we talk about growth and no growth. Like I've mentioned, there's really nothing to it. It's just a matter of holding the bottle up and seeing, did it grow, did it not grow? But some products have a sterility claim that is specific. Let's say I have a tubing set. I might claim only the fluid pathway of the tubing set as being sterile. So for example, maybe I have a syringe, such as is pictured here. So I might only claim the fluid pathway for the syringe and needle as sterile. So we would generally do sterility testing just on that portion. But the ISO 11737-2 sterility standard as it revised has some additional requirements in it that make that problematic to the point where we really can't do it. So the new requirement is if I'm extracting for a test of sterility, so for example, if I'm only flushing this tube, then I have to do a recovery efficiency, just like I would for bioburden. And then it says to perform a documented risk assessment and outcome of that risk assessment. It doesn't really give any other guidance. So what the issue we have is, okay, if I do a sterility where I do just the fluid path, and as such, I'm just flushing the tube. I'm not leaving it exposed like here in this example. If I'm just flushing it, and I have a 50% recovery efficiency, well, how do I do that? How do I address that in a risk assessment? Do I test twice as many samples because it's a 50% recovery efficiency? So I test 50% more samples for my test to sterility. Do I consider that I can only detect half potentially of the organisms of my test to sterility acceptable as far as showing my sterility's okay? There's no additional guidance in the standard, and as such, there's really no industry approach on how to do that risk assessment. Nobody's really willing to say, well, I have a 50% recovery efficiency, and that's okay for my test to sterility, my sterility passed, and therefore my product's sterile. Nobody has really been willing to put that forward at this point on what a risk assessment or what even the testing or additional testing would look like. So for right now, what the pretty much entire industry has done is we've bypassed the problem. So I can tell you right now, if you have a product that has a fluid pathway only claim, that's great. We're probably going to validate though both inside and out. So using kind of this syringe example, if your sterility claim was only fluid pathway, that's fine that you're claiming that. But for testing purposes, we're going to have to immerse the entire thing testing inside and out. And that's just something to be mindful of with the new revision of the standard, is we do kind of have that additional requirement when it comes to some of the things like a fluid pathway claim of sterility. So let's talk about BF a little bit more, because just like recovery efficiency, your dose setting and how the dose is set flows through that recovery efficiency and that bioburden estimate. Your test of sterility is really only valid with an acceptable BF test, bacteriostasis fungistasis, also called the sterility method suitability. So your entire validation really relies on and depends on demonstrating that sterility. So your entire sterility test and all those results rely on an acceptable and passing BF test. So the BF test is absolutely going to be a critical point that auditors are going to look at. So for that bacteriostasis fungistasis test, that method suitability, generally, we are going to use the 3 challenge organisms if it is a aerobic only test. So generally, that's going to be the Bacillus, the Aspergillus, the Candida albicans. And as we kind of had mentioned earlier, and for those that are joining late, generally for terminally sterilized product, we're really only going to be concerned with those aerobic organisms because most of the time our manufacturing environment, our product is not anaerobic. It's not being held under anaerobic conditions. So the organisms we expect to recover are aerobic organisms or facultative aerobic organisms, both of which are able to grow on the aerobic media. So the Bacillus, the Aspergillus, the Candida, those are our challenge organisms, and we're going to use SCDB. So the exception is going to be if we suspect or we have obligate anaerobes, such as if we have tissue or tissue-based products. In that situation, we're going to test using a second media, and we're going to use the full 6 BF organisms. But what we're going to do is we're going to take the product and we're going to place it into the exact same growth media at the same volume as the test of sterility is performed, and we're going to spike with these challenge organisms. So we're going to use 3 different testing containers, 1 for each challenge organism, and these organisms must grow within that 5-day period and be comparable to our challenge. If they do not grow, then that is an indication that that product, as tested, is inhibiting those microorganisms. That means when we have a sterility negative, we don't know, is it a sterility negative because it's sterile, or is it a sterility negative because that organism just can't grow? So we're going to have to address that. So generally, there's going to be some level of us either trying to neutralize it with neutralizing whatever the inhibitory substance is. We can try diluting it, so increasing our sterility testing volume. That only works to a point because we only have containers so large, or kind of a combination of the two. We might try a neutralizer and we might just throw all the volume we can at it. So one of the things that's kind of nice is there actually is a caveat within the standard that if I cannot dilute it and get acceptable results, if I cannot neutralize it and get acceptable results, then I minimize the effects as much as possible and I can proceed with testing. Now, the key here is, yes, I need to minimize the effects as much as possible. And that's where the term due diligence comes in again, is you're not just going to get one test, show that it didn't pass, and say, oh, well, this product's inhibitory. No, you're going to have to do your due diligence, which is going to be usually multiple rounds of testing so that we can try different neutralizers, different volumes, sometimes even different incubation temperatures and parameters in order to try and get acceptable results. Only after our due diligence has shown we cannot neutralize this product is when we would proceed with testing. So ISO 11737-2 does give growth conditions. Again, it states that they need to be identical to the sterility test. So whatever volume we use for our BF testing, whatever media we use for our BF testing, whatever temperature we use for our BF testing, we also have to do that for our test of sterility. And just because a product is not inhibitory for bioburden doesn't mean it won't be inhibitory for sterility, and vice versa. So a bioburden test, a lot of times, like we were kind of showing in the video, we're trying to get organisms off the product and into that solution, and then we're filtering that solution away in most cases. In a lot of cases, that means that we are potentially filtering away inhibitory substances. So that could potentially be a good thing. So the flip side of that is sometimes those inhibitory substances actually become concentrated on that filter. Now it's more inhibitory than it was. Whereas a test of sterility, I'm not generally filtering anywhere. I'm taking the product, I'm putting it in the bottle. That inhibitory substance is either being neutralized or it's being diluted out. So one test does not correlate to the other. Just because I have an acceptable sterility method suitability doesn't mean I have an acceptable bioburn method suitability, and vice versa. They're very different tests in that aspect. The exception being our most probable number test. That test can share the sterility method suitability as it is basically the same test. So we're going to put it into growth media at a set temperature, and generally we're going to make that media and that volume match this test of sterility and the MPN test so that we can use that method suitability in both situations. So method suitability, there's 3 different times that we can do method suitability. So the first is we can do it prior to sterility testing with dedicated test articles. We're doing 3 challenge organisms, so at a minimum, we need 3 samples to do that. So the next is we can do it concurrently to the test of sterility with, again, 3 dedicated samples. And then finally, we can do the BF test after sterility testing. And we would essentially take 3 of the samples from the test of sterility and reuse them for the BF test. But there's some caveats to all of this. So what does it mean, for example, if we have an issue where post-sterility, we do a post-sterility test, we've already done the sterility. If that BF fails, then our entire sterility test is now called into question. So potentially, we've just done our sterility test, now it's inhibitory, our entire sterility is now invalid. Even if we do it concurrently to the sterility test, the BF's probably going to get done and we're going to invalidate our sterility results. So if we have a product that we suspect or we know is inhibitory, we're going to want to do that testing prior to the test of sterility so we can ensure we're properly neutralizing the product so that we can ensure that we have passing results before we move on to the expense and time of sterility testing. The worst case is if we do a post-sterility BF, that's kind of your worst case if the BF fails because we've gone through the full 14 days of your sterility test, plus potentially the next 5 days for your BF test. So we've potentially spent 3 weeks finding out all of your results are invalid. That's a very long time and a very big loss. So if you suspect or you know that your product's inhibitory or has inhibitory substances, let us know. And this is also where, kind of telling a little bit of a story, medical grade is kind of a meaningless term. So we asked a sponsor before, hey, is there anything in your product that is inhibitory? And they said no. And they failed their BF. And we went through multiple iterations trying to neutralize it because they didn't know what was potentially inhibitory. They're like, well, there shouldn't be anything in it that's inhibitory. So we tried various neutralizers, kind of just taking shots in the dark. And then finally, they got a hold of their material list and they sent it over to me. And one of the ingredients was actually an antibiotic. It had an antibiotic coating. And when we inquired about it, the individual said, well, everything in it should be medical grade. Yes, there are medical grade antibiotics. That's kind of the point, is it's an antibiotic, it's killing bacteria. And yes, I should hope it's quote unquote medical grade so that people can take it and feel safe about that antibiotic. So medical grade does not just mean it's suddenly safe or it's biocompatible or it's microbial compatible. So if you don't know if there's an inhibitory substance and you don't know what inhibitory substances are, whether it's a chemical agent or whether it's an antibiotic, let us know what is in it so that we can kind of do at least an estimate based on kind of our experience and various materials we've seen so that we can try and take the necessary action to neutralize it and so that we don't jump to sterility testing and invalidate those results because of a failing BF. We want to do that testing ahead of time. So kind of a working example, again, taking your data so that you can see what that looks like. So we have our 3 challenge organisms. We have Bacillus, Aspergillus, Candida, and we take a titer. We see what was the amount that we inoculated in. So it's a requirement that that be under 100. So we're showing that yes, our titer was less than 100. So we have our test, and positive means yes, it grew. Positive means the control grew. They're comparable. So this is great. This means we don't have inhibition. If we have a negative in the test, that's an indication that we have inhibition. If we have a negative in the control, that means we have an issue either with our test system and we should retest, or potentially we actually have a media or a media batch that came through that is inhibitory itself. Again, that's generally not indicative of your product. So if we have a control failure, that's usually an indication that something bad happened on the laboratory side and we need to retest. The main one is if you have a negative on your test, that generally means your product is inhibitory as tested. So we need to neutralize, dilute, or something along those lines. Then that's going to lead into your sterility testing. As we mentioned, we're generally going to test 10 samples for VD Max. We're going to test 100 for method 1. And that's really going to look very similar. So units tested 1 through 10, you can imagine if we have a method 1, it's just going to say 1 through 100. We have 10 negative for growth here. If we did a method 1 and we have 100 samples, it's just going to say, hopefully, 100 negative for growth. If we do have growth, generally we're going to indicate those additionally in the table. But this is basically what your data looks like and is going to look like on a final report. So you can see and kind of understand what that BF actually looks like when you see that final report. So that's kind of our questions about the foundation. We've got the basics of a sterilization. We kind of have an understanding of VDMAX. So that's kind of building our foundation. We're going to move into radiation validations and dose audits. But before we move away from the foundation and into the validations, I want to see if there's any questions.
I'll ask another one.
Yeah.
So your, I guess, example with respect to some products claiming like only the fluid pathway is sterile, I'm puzzled by that concept because I thought that by performing sterilization validation, you're demonstrating that anything that is within the sterile packaging is considered sterile. So if you were to try to claim that only part of the medical device is sterile, don't microbes have the potential to like move after sterilization? So like, I'm just confused by that.
They might move, but it's generally short distances. So if I have something such as a IV tubing set, and I'm only claiming the inside of the tubing set is sterile, then that is kind of what I validate and what I sterilize. And to kind of get to your, well, what about if something moves or something like that? That comes into your sterile barrier and your sterile label claim. So generally, such as tubing set is going to have something that is blocking off that fluid pathway, whether that is caps that are doing it, whether that is a peel off tab, something like that, that is creating a physical barrier.
Okay, that's helpful.
So because there's a barrier, it would probably be a gamma sterilization, right?
It's gamma, E-beam, X-ray, it's all the same. If it's
Yeah,
able
yeah.
to go through your carton, it's able to go through your little tab. But generally speaking, yes, it is going to be generally fluid pathway items are radiation items because they are able to get to that fluid pathway. EO's just going everywhere, so why not just validate everything?
Thanks.
Nicole, did you have another question?
No, I'm all set. Thanks.
Okay. So when we're talking about radiation sterilization, we have to get into what is the question in a radiation validation or dose audit. So when we're talking about radiation, the question is, are my microorganisms tough? Are my microorganisms wimpy? And I like to pause for a second. I have this picture up for very much a reason. So this is one of our senior experts, Martel Winters. He's been with the company for many years and he knows sterilization very well. And he makes a great Pee Wee Herman. And if you ever have a chance to meet Martel Winters, please feel free to ask him to do the Pee Wee Herman laugh. I highly encourage that. Or when it comes to my product, are my microorganisms a mix of the two? So what this really comes down to is a game of would you rather? But the question is, would you rather be locked in a cage with one hungry and angry tiger, or would you rather be locked into a cage with 1,000 hungry and angry cats? Well, reality is both are going to be bad situations. If I have 1,000 cats, if you consider, well, one cat, let's say it's just 10 pounds on average. Now I have 10,000 of them. That's 10,000 pounds of very many sets of teeth coming at me. If I have one tiger coming at me, that's also several hundred pounds of a set of teeth coming at me. Both are going to be bad situations. So that really gets us kind of into characterization and why characterizing our bioburden matters. And this is very important and very relevant as this is the new ISO 11137-1 2025 standard. This standard actually only came out a few months ago. So when it comes to sterilization, the amount of bioburden and the types of bioburden matter. What I hopefully have is essentially one kitten that I have to take on, or nothing at all. What I really don't want is to be taking on 1,000 tigers. So I want my amount of bioburden to be low, and I want the resistance of my bioburden to be low. So that's where we're going to get into characterization and some of the brand new guidance from the standard. So the new clause 7.2 states the effectiveness of the system shall be demonstrated and shall include determination of bioburden, including characterization, and also establishment of bioburden alert and action levels in accordance with the ISO 117. I got that typing wrong, but it should be 11737-1 standard. I put one too many threes in there. So it is required that you establish bioburden alert and action levels and that you include determination of bioburden, including characterization. So the key, including characterization, and it is a requirement, and bioburden alert and action levels are a requirement. So it expands on this in the informative annex that corresponds with that clause. So demonstration of stability in bioburden numbers and types is critical for radiation sterilization. This is best achieved by engaging personnel who are competent in microbiology and sterility assurance throughout the manufacturing of the product and its data interpretation. So the short version, characterization is a requirement for radiation sterilization, and setting alert and action levels are requirements for radiation sterilization, because we need to know, we need to look at those microorganisms and we kind of need to characterize them so we know whether we have the tiger or whether we have the cat. We need to know whether we have 1,000 tigers or 1,000 cats. We need to know if it's one highly resistant organism or one very puny microorganism. So characterization is very important. And with that, we also want to talk about, with characterization, again, that competent personnel is going to be really what matters so that we can customize it to your product and process. The more bioburden data we can build over time, the more we understand what we refer as our microbial library. And we have an understanding, is this organisms I've seen before? And have I been able to deal with them before? Or are these brand new organisms and I have a high degree of resistance? So I see there's a question. Yes, Scott.
Maybe this is coming up in a future slide, but if you could give us more details about setting alert and action levels and whether the expectation is to take it all the way down to that characterization level.
So alert and action levels have to do with our numbers, and then characterization is our type. So they are going to be two separate things, but an alert level may trigger us to do something such as additional characterization. So, for example, if I have a product that routinely has a bioburden of, we're going to use about 50 CFU, sterilization VD max wise, I really, from a sterilization perspective, that's logarithmic. So if I'm is within my log, as long as I'm not going, example, over 100 CFU, I'm generally going to be fine. So we want to set our alert and action levels kind of appropriately and accordingly. Now, there is not a set way to set alert and action levels. Nelson Laboratories does have some additional guidance on the Sotera Health Academy that you can take a look at. It's also a consulting service that we offer. But setting your alert and action levels is really going to be based on your product and your sterilization. I'm going to want to set much tighter alert and action levels for a bioburden state-based sterilization than I am for an overkill-based sterilization. I also am going to want to set tighter bioburden alert and action levels, maybe depending on how I set my bioburden-based method. So for method 1, my bioburden amount and my sterilization dose are directly correlated. So I probably want to set a tighter alert and action level for that than I would say for potentially something like a VD Max, where it's a tiered approach. And I have, because of that tier, a little bit of overkill set in. Now, as far as characterization goes, that's going to be somewhat separate. You're going to want to build your microbial library and do characterization on an ongoing basis. So you might do more testing up front to understand what microorganisms you have and what you're seeing on a routine basis, and then do kind of routine monitoring to make sure that that's staying stable over time so that my types of microorganisms aren't changing. So with that, fortunately, and we will talk about that when we talk about failures a little bit later on, fortunately for us, when it comes to radiation, the microorganisms raise a literal and figurative red flag for us. So radiation resistant organisms tend to be pink, red, or sometimes, as we'll talk about, orange in color. But that gives us something that we can narrow down and specifically look for. So a common way to do characterization might be to do gram stain of the top 3 predominant isolates. That's going to give me a higher level gram stain. It's not the most expensive approach. And that's going to tell me what is predominantly on my product. And I'm going to be able to see, do I have mostly gram-negative rods? Do I have mostly positive cocci? And I can kind of see how that's changing in general over time. But then I might want to do something like kind of dig down a little bit and then add on to my identification something along the lines of identify any pink, red, or orange colonies detected. If there's no colonies detected, great. I don't need to do that level of identification. If there are those pink, red, or orange, I can look and I can see, is it a Staphylococcus epidermidis, which is not resistant, or is it a Deinococcus radiodurans, which is highly resistant? And a gram stain isn't going to tell me necessarily the difference between Staph epi and Deinococcus. Both are positive cocci. So that's when something such as pink, red, and orange CFU and having it fully identified can tell me what I'm actually dealing with. So alert and action levels tells me how many of something I have and gives me kind of a bit of a fence to build around that. And then the characterization tells me, am I fencing up tigers or am I fencing up cats? So they're related but separate.
That's really helpful, Bryce, to help me understand that they're related and separate. And then a note for the library team, as we work to come into compliance to this new version, I think that we've got, at least in some facilities, we've got some gaps relative to characterization that we're going to need to think about.
And as I also mentioned, as you're kind of considering that and bringing into compliance, testing up front does not have to be testing forever. So generally speaking, you do want to see how the bioburden is going to change over time. The characterization, for example, is probably going to change some with the seasons. You're probably going to see, for example, more molds, yeasts, things like that in the autumn. You're probably going to see more water bugs, for example, Pseudomonas, during the rainy season, springtime, for example. So your bioburden, the nature of your bioburden is going to change over time, but that's also going to give us kind of our basis for setting our initial library. Is we might want to do a lot of initial testing over the course of that year. And then once we have that year's worth of data, then we can kind of back off that our testing and compare and see how does it compare to our previous year? Is it different? If so, if it is different, how so? If not, then great, it's not different, and that kind of tells us what we need to know. So testing up front, good to build your base, does not mean that you have to continue that testing indefinitely, though.
Thank you for all that.
So let's talk about our validation methods. Oh, there's another question.
Sorry, we have one in the room.
Yeah, I had a
Yeah.
question in terms of if you have products in terms of families, will that be affected with this characterization, or are you able to still leverage?
So
yeah.
the answer is yes, you can still do family groups. A key of building a family group, which we'll get to when we talk family groups, is that the family needs to be made of comparable numbers and types of microorganisms, or we also have master products, master family groups, where we have a master product that's the worst case. So in that case, that master product would have the most organisms or the most resistant organisms. But characterization still plays a role in family groups, especially with master products. If we do have a product that for some reason it has more radiation resistant organisms, then chances are that's going to become our master product. But if we have consistent amounts of organisms and consistent types of organisms across a family group, then yes, we can family group them, and that might look more like an equivalent family group. But we do still have that alert and action level. We still do have that characterization, but it's kind of at the family level.
Okay, thank you.
So I am going to pause a minute. I think now would be a good time to take a bit of a break. I need to actually check the batteries on my headset. So we'll pause for about 15 minutes. So we'll come back. Let's see. We'll come back at 50 minutes after, so we'll pause. If you do have questions, please put them in the chat. In the meantime, I am going to swap out the batteries in my headset. I do apologize if that causes me to disconnect. Don't worry, I'll reconnect before we restart back up.
Bryce, it does sound like this is going past 1 o'clock. Do you know how late this will be going?
We should. Well, I'm not sure of the time zone difference, but the current planned time, we're actually on track for ending on time for what we put in the meeting invite.
Okay, thanks.